January 12, 1940. Mare Island Naval Shipyard, Vallejo, California. A foreman penciled totals on a hull outfitting ledger while electric torches flared along a destroyer escort's bulkheads, throwing orange light across steel plates still warm from welding. In the administrative offices, procurement clerks reviewed production schedules that showed a troubling pattern. Welding times had improved dramatically, but outfitting, the labor-intensive process of attaching thousands of studs, hangers, and fixtures, remained a persistent bottleneck. Navy planners expected electric arc welding to solve construction delays. The statistics told a different story. Yard records documented rising man-hours per completed hull section as work shifted to tight interior spaces requiring scaffolding, drilling, and manual bolt installation. One welder watched the inefficiency with growing frustration. Within months, his garage workshop would produce a solution. The Navy would initially reject, a device that would eventually help build the arsenal that won the war. Theodore Ted Nelson had worked at Mare Island since 1938, $11 per day. His job involved joining steel plates for destroyer escorts and submarine components, precision work in cramped, poorly ventilated spaces. By January 1940, he had witnessed firsthand how traditional construction methods created predictable delays. The shipyard's transition from riveting to electric arc welding had accelerated hull assembly significantly. A riveting crew of 4 men working 8 hours could join approximately 50 feet of seam. 2 welders, using modern equipment, completed the same work in 3 hours. Navy efficiency experts celebrated these gains. But the statistics masked a growing problem. Each destroyer escort required over 12,000 individual studs, brackets, and hangers to support piping, electrical conduits, ventilation ducts, and equipment mounting. Installing these attachments demanded drilling through steel plate, inserting threaded studs, securing nuts. The process required scaffolding for overhead work and consumed enormous labor hours that welding improvements couldn't touch. Mare Island's production records from 1940 documented the bottleneck clearly. Hull welding, 38% of construction man-hours. Outfitting, 47%. The numbers revealed that faster hull joining had merely shifted the critical path rather than eliminating delays. Nelson understood the mathematics. Each drilled and bolted stud required 15 to 20 minutes of skilled labor. Multiply by 12,000 studs per ship. The result? 4,000 man-hours of outfitting alone, equivalent to one worker laboring full-time for 2 years. The problem compounded in confined spaces. Installing studs on overhead surfaces or inside tight compartments required scaffolding, special lighting, awkward positioning. Welders reported that 30% of their outfitting time involved setup and access preparation rather than actual attachment work. Injury rates climbed. Workers balanced on platforms while operating heavy drills. Nelson recognized that drilling represented the fundamental inefficiency. The process removed metal that welding could theoretically replace, but existing arc welding techniques proved unreliable for attaching studs. Traditional stick welding produced excessive heat that warped thin studs before achieving proper fusion. Attempts to weld studs often resulted in weak joints that failed Navy inspection standards. Trade journals from 1939 and 1940 contained scattered references to arc-drawn stud attachment methods used in bridge construction. Experimental processes showed promise, but they remained far too slow and inconsistent for naval applications. Navy Bureau engineers considered the technology unproven. By March 1940, Nelson had formed a clear vision. If studs could be welded rather than drilled and bolted, installation time might drop from 15 minutes to under 1 minute per attachment. The labor savings would prove enormous. Developing such a process would require equipment that did not yet exist. Nelson's residential garage in Vallejo became an improvised research facility during evening hours and weekends. A bench vise held test steel plates. A transformer salvaged from surplus equipment provided controlled electrical power. His goal: achieve instantaneous fusion between stud and plate without the excessive heat buildup that plagued conventional welding. The breakthrough concept involved 3 integrated elements. First, a spring-loaded mechanism would drive the stud against the base plate with precise force. Second, a timed electrical discharge would create an arc between stud and plate, melting both surfaces simultaneously. Third, a ceramic ferrule would surround the stud tip, containing the molten metal and shielding the arc from air contamination. Nelson's first prototype achieved partial success in May 1940. The spring plunger drove the stud correctly. The electrical discharge created fusion, but without proper shielding, the resulting welds proved porous and weak. Navy specifications required stud attachments to withstand pull forces exceeding 5,000 pounds. Early tests showed failure at less than 2,000. The ceramic ferrule solved the shielding problem. By surrounding the stud with a disposable ceramic ring during welding, Nelson created a sealed chamber that prevented oxygen from contaminating the molten pool. The ferrule also concentrated heat at the fusion point rather than allowing it to disperse through the stud shaft. Refined prototypes tested in August 1941 achieved remarkable results. Welding time per stud, under 1 second. Pull tests, consistently exceeding 6,000 pounds, 20% above Navy minimum requirements. The process required no drilling, no threaded hardware, minimal cleanup. Each successful weld consumed one ceramic ferrule, costing approximately 3 cents. Nelson documented his findings methodically. Test logs recorded timing, pull strength, plate thickness, stud diameter, and current settings for hundreds of sample welds. Photographs showed cross-sections revealing complete fusion between stud and base metal. The evidence demonstrated that his process could revolutionize shipyard outfitting procedures. But transforming a garage prototype into production equipment required resources Nelson could not provide alone. Industrial-grade power supplies, engineered spring mechanisms, quality-controlled ferrule production demanded significant capital investment. The Navy represented the only realistic customer. In October 1941, Nelson prepared a demonstration for Navy technical inspectors at Mare Island. Sample plates showing various stud configurations, pull test results, timing records. The presentation would determine whether his innovation received official consideration or remained a welder's interesting experiment. November 5, 1941. 3 Bureau engineers observed as Nelson demonstrated his stud welding process on sample plates. The welding gun attached studs in less than a second each. Pull tests confirmed strengths exceeding specifications. The ceramic ferrules left minimal slag, requiring quick cleanup. Bureau engineers acknowledged the technical achievement. Then came the concerns, reliability questions, training overhead. Their report noted that manual drilling and bolting, while slow, produced consistent results with established procedures. Introducing unproven welding methods into critical hull construction presented unacceptable risks. The official recommendation: process shows promise for future evaluation, but is not recommended for adoption in current construction programs. Nelson faced a fundamental choice: continue working as a shipyard welder, accepting that his innovation would remain shelved indefinitely, or risk his financial security to commercialize the technology independently. December 1, 1941. Nelson resigned from Mare Island. Using personal savings and a $95,000 loan secured against his home and family assets, he established Nelson's Stud Welding Company in a rented industrial space. The decision transferred all development risk from the Navy to one individual. The new company's immediate priorities: engineering production versions of the welding gun, designing reliable power supplies, developing ceramic ferrule manufacturing processes. Nelson hired 3 machinists and 2 electrical technicians, paying wages from borrowed funds with no guarantee of future contracts. By early December, the company had produced 6 functional stud welding units and several thousand test ferrules. Nelson prepared marketing materials targeting both naval shipyards and commercial fabricators. His financial model assumed that industrial users would recognize the labor savings and adopt the technology gradually. December 7, 1941. Japanese naval aircraft attacked Pearl Harbor. The United States entered the Second World War. Within weeks, shipyard construction schedules would shift from peacetime production to emergency mobilization. The procurement environment that had rejected Nelson's innovation was about to change fundamentally. December 8 brought transformation to American shipbuilding. Teletypes clattered in Navy procurement offices as mobilization orders arrived from Washington. Existing construction programs received immediate authorization to expand by 300 to 500%. New emergency shipyards would be established at locations across both coasts. Peacetime assumptions evaporated. Mare Island's December production schedule called for completing 4 destroyer escorts during the first quarter of 1942. The revised mobilization plan demanded 12 ships by June. Similar expansions affected every naval shipyard, from Maine to California. The U.S. Maritime Commission received orders to produce a new class of standardized cargo vessels, Liberty ships, at rates exceeding 100 hulls annually. Pre-war planning had assumed steady workforce growth and gradual facility expansion. War orders demanded immediate output increases using existing infrastructure. Shipyard managers faced an impossible equation: triple production without corresponding increases in skilled workers or construction time per vessel. Liberty ship construction illustrated the challenge starkly. Each vessel required approximately 1,200,000 man-hours using traditional methods. At that rate, building 100 ships annually demanded 600 full-time workers per ship under construction, a workforce exceeding 60,000 people for the program alone. The United States possessed neither that many trained shipbuilders nor time to develop them. The Maritime Commission's response involved radical standardization and prefabrication. Liberty ships would use identical designs, welded construction, and modular assembly. Sections built in separate facilities would be transported to final assembly yards. The approach dramatically reduced skilled labor requirements. But prefabrication and welding solved only hull assembly challenges. Each Liberty ship still required approximately 15,000 studs, hangers, and brackets to support pipes, cables, ventilation, and equipment. Installing these attachments using traditional drilling consumed over 80,000 man-hours per vessel, nearly 7% of total construction time. Outfitting represented the new critical path. Welders could join hull sections rapidly. Attachment work remained stubbornly slow. Shipyard supervisors reported that skilled workers spent increasing portions of their shifts positioning scaffolding, drilling holes, managing hardware, everything except actual construction. Nelson's Stud Welding Company received its first inquiry on December 15, 1941. A procurement officer from San Francisco's Naval District had heard of the rejected prototype. He wanted to observe a demonstration. War mobilization had transformed unproven technology from liability into potential solution. The stakes had changed completely. In peacetime, Navy bureaus could afford to wait years for new technologies to mature. In war, any process that might accelerate construction demanded immediate evaluation. Nelson's garage experiment now represented a possible answer to the Maritime Commission's most pressing bottleneck. February 3, 1942. Technical inspectors arrived at Nelson's workshop in Vallejo. The demonstration would determine whether his welding process received serious consideration or remained an interesting but impractical innovation. Maritime Commission engineers arrived, expecting marginal improvements over existing methods. Nelson had prepared a section of ship plate representing typical outfitting challenges: overhead studs requiring scaffolding access, closely spaced attachments for cable runs, heavy-duty mounts for equipment. Using traditional drilling and bolting, such work would consume approximately 4 hours for a skilled crew. The welding demonstration began at 0900 hours. Nelson's assistant positioned the welding gun against the first stud location. A brief electrical discharge, lasting less than 1 second, fused the stud to the plate. Pull testing confirmed strength exceeding 6,000 pounds. The ceramic ferrule dropped away, leaving a clean weld requiring minimal grinding. Engineers watched as Nelson completed 50 studs in 43 minutes. Average, 52 seconds per attachment, including positioning time. The pace seemed almost impossible compared to drilling methods requiring 15 minutes per stud. Quality inspection revealed consistent fusion, no rejected welds. Technical questions focused on reliability and scalability. Could operators maintain quality under production pressure? Would ferrule supply chains support high-volume manufacturing? What training time would new welders require? Nelson provided test logs documenting hundreds of successful attachments and detailed material costs per weld. The economic analysis proved compelling. Each drilled stud, 15 minutes of labor, plus drill bits, bolts, and nuts. Nelson's process, 1 minute plus a 3-cent ferrule. For a Liberty ship requiring 15,000 attachments, the time savings exceeded 3,000 man-hours per vessel. That translated to 2 workers laboring full-time for 9 months. Maritime Commission engineers prepared their evaluation report immediately. The document noted, "Demonstration confirms significant labor reduction in outfitting operations. Process reliability appears suitable for production application. Recommend immediate trial adoption at selected shipyards with expanded procurement if results prove satisfactory." Within a week, Nelson received his first government order, 24 stud welding units, with power supplies, 100,000 ceramic ferrules. Contract value, over $200,000 more than twice his initial investment. Delivery schedule, 90 days. The order represented validation. It also brought enormous pressure. Nelson's small company needed to transform garage-quality prototypes into production equipment meeting military specifications. Every unit would face daily use under harsh shipyard conditions. Failure would end the program immediately and leave Nelson bankrupt. April through June 1942 witnessed the integration of stud welding into American shipyards from Richmond, California, to Groton, Connecticut, and Baltimore, Maryland. The Maritime Commission distributed Nelson's equipment to yards building Liberty ships, destroyer escorts, and submarines. Each installation represented a test of whether garage innovation could survive industrial-scale demands. Richmond Shipyard No. 2 received 6 welding units in mid-April. Supervisors selected experienced welders for initial training, expecting weeks of practice before productive work began. The actual training cycle surprised everyone. 4 hours. After 4 hours of instruction covering gun operation, ferrule placement, and safety procedures, welders began production work. By the second day, most operators achieved Nelson's demonstration speeds. Early concerns about technique difficulty proved unfounded. Unlike traditional arc welding requiring precise torch angle and speed control, stud welding involved straightforward gun placement and trigger operation. The equipment controlled all critical variables: current timing, arc length, cooling rate. Operator skill mattered primarily for positioning accuracy rather than welding technique. Quality control reports from Richmond documented the process advantage clearly. Traditional drilling and bolting showed reject rates averaging 8% due to misaligned holes, damaged threads, loose fittings. Stud welding reject rates measured below 2%, primarily from incorrect initial positioning rather than weld failure. The ceramic ferrule system proved remarkably consistent. Groton's Electric Boat Shipyard, specializing in submarine construction, reported even more dramatic improvements. Submarine pressure hulls required thousands of precisely located attachment points in confined spaces barely accessible to workers. Traditional drilling demanded elaborate scaffolding and multiple shifts to complete single compartments. Stud welding transformed submarine outfitting. Welders could access tight spaces with the compact gun, position studs quickly, achieve full-strength welds in seconds. Electric Boat's production logs showed outfitting time per submarine pressure hull section declining from 12 days to 3 days between March and June 1942. Baltimore's Bethlehem Steel facility integrated the process into Liberty ship prefabrication. Rather than outfitting completed hulls, workers attached studs to individual steel sections before assembly. The approach allowed parallel work on dozens of ship modules simultaneously. Stud welding enabled rapid attachment without drilling that weakened pre-welded seams. By July, shipyard supervisors reported an unexpected secondary benefit. Traditional drilling and scaffolding work had generated high injury rates from falls, metal chips, equipment handling. Stud welding eliminated most scaffolding requirements and produced minimal debris. Accident reports showed injury reductions exceeding 30% in outfitting departments. Nelson's company struggled to meet accelerating demand. The initial order of 24 units expanded to 90 units by May, then 200 by July. Manufacturing capacity represented the new bottleneck. Nelson secured contracts with precision machine shops for welding gun components and negotiated ceramic ferrule production with multiple suppliers. Material logistics required constant attention. Each welding gun consumed approximately 200 ferrules daily under production conditions. A major shipyard with 12 guns needed 10,000 ferrules weekly. Ceramic manufacturing, quality inspection, packaging became as critical as welding equipment production. By August 1942, over 150 Nelson stud welding units operated across American shipyards. The garage prototype had evolved into standard industrial equipment. The real test would come as Liberty ship production accelerated toward the Maritime Commission's ambitious targets. October 21, 1942, Richmond Shipyard No. 2 completed the Liberty ship Robert E. Peary in 4 days, 15 hours, and 29 minutes from keel laying to launch, a construction speed that shattered all previous records. The achievement demonstrated what coordinated prefabrication, welding, and efficient outfitting could accomplish. The Peary's construction incorporated every innovation the Maritime Commission had developed. Prefabricated sections arrived at the assembly site, ready for final joining. Hull welding teams worked continuously across multiple shifts. Outfitting proceeded simultaneously with hull assembly, using stud welding to install attachments without drilling delays. Traditional Liberty ship construction required approximately 230 days from start to launch. The Peary achieved launch-ready status in under 5 days, a 50-fold improvement. While such extreme speed represented demonstration rather than sustainable production, the record proved that systematic optimization could achieve results previously considered impossible. Stud welding contributed measurably to the achievement. Outfitting work that normally consumed 3 weeks proceeded in parallel with hull assembly across just 4 days. Welders installed over 15,000 studs during that period, an average rate exceeding 3,000 attachments daily. The pace would have been physically impossible using drilling methods. Kaiser shipyards, operating multiple facilities in Richmond and Portland, expanded stud welding adoption aggressively through late 1942 and early 1943. Henry Kaiser's management philosophy emphasized removing bottlenecks through any means necessary. Nelson's technology aligned perfectly with that approach. By November 1942, Kaiser shipyards operated over 80 stud welding units across their facilities. Production data showed clear correlation between stud welding adoption and overall construction time reduction. Yards using the technology consistently achieved Liberty ship completion in 45 to 60 days. Yards relying primarily on traditional methods required 75 to 90 days. The statistical evidence prompted Maritime Commission directives in December 1942 recommending stud welding for all new construction. While not mandatory, the recommendation carried weight equivalent to requirement. Shipyard managers understood that falling behind productivity benchmarks would invite unwanted scrutiny. Liberty ship production statistics for 1942 documented unprecedented industrial achievement. American shipyards launched 646 vessels during the year, more than triple the output of all Axis nations combined. Construction time per ship declined from 230 days in January to 70 days by December. That 70-day average concealed wide variation. The fastest yards achieved completion in 42 days. Slower facilities required 90 days or more. Maritime Commission analysis identified outfitting efficiency as the primary variable distinguishing high and low performers. Yards using stud welding consistently ranked in the top quartile. Nelson's company expanded dramatically to meet demand. By January 1943, employment exceeded 200 workers, manufacturing, welding guns, power supplies, coordinating ferrule production. Monthly output reached 150 welding units, plus 3 million ceramic ferrules. The garage workshop had become a significant defense contractor. Financial transformation accompanied industrial growth. The $95,000 loan Nelson secured in December 1941 had generated over $8 million in government contracts by early 1943. The company achieved profitability in May 1942 and maintained strong margins throughout the expansion. The most significant impact measured beyond dollars or production statistics. In May 1943, Navy Bureau of Ships published a comprehensive analysis of wartime shipbuilding improvements. The report stated, stud welding has reduced outfitting times by 70% compared to traditional methods. The process represents one of the war's most significant industrial innovations. 1943 witnessed stud welding's expansion beyond Liberty ships into submarine construction and naval vessel outfitting. Portland's shipyards and Groton's electric boat facility maintain detailed records tracking the technology's impact on submarine production schedules and quality metrics. Submarine construction presented unique challenges requiring precision beyond Liberty ship standards. Pressure hull integrity permitted zero tolerance for drilling errors or weakened sections. Each attachment point needed verification to withstand deep diving pressures. Traditional drilling methods required extensive quality control and frequent rework. Stud welding proved ideally suited for submarine applications. The process created attachments without removing base metal that contributed to pressure hull strength. Welds achieved consistent quality, requiring minimal inspection beyond standard pull testing. The compact equipment accessed confined spaces inside pressure hulls that scaffolding could barely reach. Production statistics documented the transformation clearly. U.S. submarine output rose from 22 boats in 1941 to 73 in 1943, more than tripling in 2 years. Electric boats' contribution accelerated from approximately 1 submarine monthly in early 1942 to 3 submarines monthly by mid-1943. Groton's production logs attributed significant time savings to stud welding adoption. Outfitting a Gato-class submarine pressure hull section required approximately 900 man-hours using traditional drilling. Stud welding reduced that figure to 270 man-hours, matching the 70% reduction the Maritime Commission found for Liberty ships. The acceleration affected Pacific naval strategy directly. Admiral Chester Nimitz's island-hopping campaign relied heavily on submarine interdiction of Japanese supply lines. Each additional submarine operational by mid-1943 represented hundreds of thousands of tons of enemy shipping potentially destroyed. Faster construction translated directly to enhanced combat capability. Naval analysts estimated that stud welding contributed to approximately 30 additional submarines entering service during 1943, compared to projections based on traditional construction methods. Those 30 boats sank over 1 million tons of Japanese merchant, shipping roughly 5% of total Allied submarine warfare effectiveness that year. Destroyer escort production benefited similarly. These anti-submarine vessels required rapid construction to counter German U-boat threats in the Atlantic. Mare Island, Boston Navy Yard, and Philadelphia's facilities used stud welding extensively for destroyer escort outfitting, achieving completion times approaching 90 days from keel to commissioning. By late 1943, virtually every American naval shipyard incorporated stud welding as standard practice. Training programs taught the technique to new workers entering shipbuilding trades. Equipment manufacturers beyond Nelson's company received licenses to produce compatible welding guns and ferrules, expanding capacity to meet sustained demand. The technology's classification, as restricted under wartime secrecy protocols, prevented public recognition but ensured secure information control. Nelson's patent applications proceeded through military review channels rather than standard civilian processes. Publication would wait until after the war's conclusion. 1943 through 1944 brought comprehensive Navy analysis of wartime shipbuilding innovations. The Bureau of Ships established review boards to document production improvements and calculate their contributions to overall military effectiveness. Stud welding received detailed examination as one of the war's most impactful industrial processes. Statistical compilation began in March 1943 and continued through August 1944. Auditors examined production records from every major shipyard, construction times, labor allocations, quality metrics, cost analyses. The data revealed patterns that demonstrated stud welding's comprehensive impact. By December 1944, American shipyards had completed 2,710 Liberty ships since program inception. An additional 203 submarines had entered service. Destroyer, escorts, fleet destroyers, other naval vessels added thousands more completed hulls. Nearly every vessel built after May 1942 incorporated stud welding technology. Bureau of Ships analysts calculated aggregate labor savings by comparing actual construction times against estimates based on traditional drilling methods. The analysis assumed that without stud welding, outfitting would have consumed approximately 70% more man-hours per vessel across all ship types. The resulting figures staggered even experienced naval administrators. Total estimated labor savings exceeded 50 million man-hours across all shipbuilding programs. That calculation represented the equivalent of 25,000 workers laboring full-time for an entire year. Workforce equivalent to the population of a medium-sized city. Alternative analysis examined what those saved hours enabled. 50 million man-hours translated to approximately 15,000 additional ship construction months using average productivity figures. In practical terms, stud welding had provided labor capacity equivalent to building roughly 250 additional Liberty ships beyond actual production. The comparison to German shipbuilding proved particularly striking. German yards, relying primarily on traditional riveting and bolting methods, completed fewer than 25 major naval vessels during 1943. American yards launched over 500 during the same period. While many factors contributed to this disparity, industrial efficiency represented a critical advantage. German naval construction suffered from systematic inefficiencies that Allied innovations had overcome. Riveting remained standard practice despite its labor intensity. Manual drilling and threading consumed enormous worker hours. Prefabrication saw limited adoption. The cumulative effect meant German shipyards required 3 to 4 times as many man-hours per vessel as American facilities. During a single-month November 1943, American shipyards launched more tonnage than German yards completed during the entire year. The disparity reflected not just resource advantages, but systematic process optimization that multiplied raw capacity into overwhelming output superiority. Bureau analysts noted that stud welding's impact extended beyond direct labor savings. The technology enabled parallel work processes previously impossible with scaffolding-dependent drilling. Quality improvements reduced rework and inspection time. Lower injury rates maintained workforce availability. These secondary effects multiplied primary time savings substantially. Stories like Nelson's, where individual ingenuity transforms industrial capacity, remind us that victory depended not just on battlefield heroics, but on countless practical innovations. If you value preserving these lesser-known chapters of history, consider supporting content that documents the engineering achievements that shaped the modern world. November 1944 brought formal recognition of Nelson's contribution to wartime production. The Navy Department awarded the E Award for Excellence in Production to Nelson Stud Welding Company, recognition reserved for contractors demonstrating exceptional achievement supporting military operations. The award ceremony at the company's expanded facility in Oakland, California, drew representatives from the Maritime Commission, Bureau of Ships, and several major shipyards. Nelson received the award flag and accompanying citation, noting the company's outstanding contribution to America's naval construction through development and manufacture of innovative welding equipment. Behind the recognition lay tension over credit attribution. Government engineers argued that military specifications and quality requirements had guided the technology's development and refinement. Nelson maintained that fundamental innovation had occurred independently before any government involvement. The dispute reflected broader wartime debates about public versus private sector contributions. Patent documentation recorded the timeline clearly. Nelson filed U.S. Patent Application Number 2,273,632 in January 1942, documenting his stud welding process with detailed technical specifications and test results. Military security classification delayed publication until 1945, after Germany's surrender. The patent application demonstrated that core innovation predated government contracts by over a year. Nelson's garage workshop had produced functional prototypes before Pearl Harbor. Navy rejection in November 1941 confirmed that government engineers initially dismissed the technology rather than developing it. Nevertheless, government technical support proved essential for large-scale deployment. Military quality standards forced refinements that improved reliability, Naval engineers contributed specifications for marine environment durability. Shipyard feedback identified practical modifications, enhancing operator efficiency. The final production technology reflected collaborative development, even if initial innovation was private. Industrial committees examining post-war patent policy debated whether wartime innovations should remain privately controlled or become public domain. Some argued that government contracts and military necessity had transformed private inventions into national assets. Others maintained that patent protection incentivized innovation and should continue regardless of wartime circumstances. Nelson's case illustrated the complexity. His $95,000 personal investment had funded initial development when government support was unavailable. Yet government contracts provided the market enabling commercial success. Without war demand, stud welding might have remained a garage experiment for decades. The patent's 1945 declassification allowed commercial applications beyond shipbuilding. Bridge construction firms expressed immediate interest in adopting the technology for structural steel assembly. Manufacturing facilities recognized potential for industrial equipment mounting. The process, once dismissed as unnecessarily risky, now appeared positioned for widespread civilian adoption. August 1945 brought both victory and accounting. Japan's surrender on August 15 ended the Second World War. Within weeks, the Maritime Commission published its final statistical report documenting American shipbuilding achievements during 4 years of industrial mobilization. The numbers captured unprecedented manufacturing scale. American shipyards completed over 6,000 naval vessels of all types between 1942 and 1945. Liberty ships alone totaled 2,710 hulls, destroyer escorts, 420, submarines, 247, fleet carriers, battleships, cruisers, support vessels added thousands more. Cumulative tonnage exceeded 28 million tons, more than twice the combined output of all other Allied nations. Peak monthly production in December 1943 delivered 140 vessels, totaling over 800,000 tons. The sustained output rate transformed American merchant and naval capacity fundamentally. Maritime Commission analysis examined the technological foundations enabling such production. Welding technology received primary emphasis, having replaced nearly 3 billion rivets during the war. Prefabrication methods earned recognition for transforming construction sequencing. Standardized designs allowed unprecedented manufacturing efficiency. Stud welding appeared prominently in the report's innovation section. The document noted labor productivity improvements in shipyard outfitting operations exceeding 70% compared to 1941 baselines. Quality metrics showed reject rate reductions and injury statistic improvements. Economic analysis calculated cost savings per vessel, averaging $8,000, modest individually, but totaling over $20 million across the entire program. Admiral Emory S. Land, chairman of the Maritime Commission, contributed a foreword to the final report that captured the production program's significance. Victory in the Second World War required not weapons alone, but the speed of their creation. American industry achieved manufacturing rates that enemies could not match and allies could not equal. This superiority determined strategic outcomes as surely as any battlefield engagement. Labor statistics revealed the human scale of achievement. Peak shipyard employment exceeded 600,000 workers, many entering industrial trades for the first time. Training programs condensed multi-year apprenticeships into months of focused instruction. Women entered welding and assembly roles previously closed to them. The workforce transformation represented social change as significant as industrial innovation. Productivity growth measured the program's technical sophistication. Average labor required per Liberty ship declined from 1,200,000 man-hours in early 1942 to 400,000 man-hours by late 1944, a threefold improvement, achieved through systematic process optimization. The statistical abstract concluded with comparative analysis of Allied and Axis production. During 1944, American shipyards alone exceeded combined German, Italian, and Japanese output by factors exceeding 10 to 1. The disparity reflected not just resource advantages but fundamentally different approaches to industrial organization and technical innovation. As Japanese surrender ceremonies proceeded aboard USS Missouri in Tokyo Bay, American merchant ships already carried occupation forces and relief supplies to devastated regions. The vessels enabling that deployment many completed months earlier, using technologies pioneered during desperate mobilization, now supported peace with the same efficiency that had supported war. 1946 through 1950 witnessed Nelson Stud Welding Company's transition from defense contractor to diversified industrial supplier. The end of naval construction contracts forced rapid adaptation to civilian markets. Nelson recognized that stud welding applications extended far beyond shipbuilding if properly marketed to new industries. Automotive manufacturing represented an immediate opportunity. Detroit's assembly lines used thousands of studs and fasteners for mounting brackets, securing trim, attaching components. Traditional methods involved drilling, threading, or spot welding, all slower than stud welding and often producing weaker attachments. Ford Motor Company conducted initial trials in March 1946, installing engine mount brackets using Nelson's equipment. The process reduced attachment time from 12 minutes per unit to 90 seconds, an 8-fold improvement. Quality testing confirmed that welded studs exceeded the strength of traditional bolted assemblies. By July, Ford had ordered 50 welding units for production deployment. General Motors followed with larger contracts in late 1946, integrating stud welding into truck frame manufacturing and body panel attachment. Chrysler adopted the technology for engine assembly operations. By 1948, stud welding had become standard practice across Detroit's major manufacturers. Construction and bridge building provided another major market. Structural steel fabricators recognized that stud welding could replace traditional drilling and bolting for attaching shear connectors, reinforcement plates, mounting brackets. The process eliminated weakening of structural members while accelerating fabrication schedules. The Bureau of Standards published a comprehensive technical analysis in 1948 that established stud welding as the accepted method for high-integrity structural fastening in applications requiring strength, speed, and reliability. The endorsement provided independent validation, supporting adoption across multiple industries. Nelson's company evolved from manufacturing solely welding equipment to licensing technology broadly. Dozens of firms received licenses to produce compatible equipment and ceramic ferrules. The business model shifted toward patent royalties, technical consulting, specialized high-performance equipment, rather than high-volume manufacturing. Financial success transformed Nelson's personal circumstances dramatically. The welder, earning $11 daily in 1940, had become president of a multi-million-dollar company by 1950. The $95,000 loan that nearly bankrupted his family had generated wealth exceeding his initial annual salary by factors approaching 1,000. Yet Nelson remained virtually unknown outside industrial circles. No monuments commemorated his contribution. Popular histories of the Second World War rarely mentioned stud welding among technological achievements. The dramatic stories of radar, code breaking, atomic weapons overshadowed quieter innovations in manufacturing processes. Nelson accepted the obscurity with characteristic pragmatism. In a rare 1949 interview with a trade journal, he stated, "The work speaks for itself through the ships built and bridges constructed. Recognition matters less than knowing the technology serves useful purposes." 1950 through the present witnessed stud welding's evolution from innovative process to ubiquitous industrial standard. The technology appears in applications ranging from skyscraper construction to shipbuilding, automotive assembly to aerospace manufacturing. Modern welding equipment descends directly from Nelson's original designs, refined through decades of incremental improvement, but fundamentally unchanged in principle. Every United States Navy vessel commissioned since 1945 incorporates components installed using stud welding technology. Aircraft carriers, submarines, destroyers, amphibious assault ships, all rely on the process for outfitting internal spaces and mounting equipment. The Navy's continued adoption validates the original wartime decision to embrace the innovation. Commercial shipyards worldwide adopted similar practices following American example. European yards integrated stud welding during post-war reconstruction. Japanese shipbuilders embraced the technology during their industrial expansion in the 1960s and 70s. Chinese shipyards adopted the process during modernization programs in the 1980s and 90s. The innovation pioneered in a California garage became global standard practice. Bridge construction transformed particularly dramatically. Major infrastructure projects from the 1950s onward used stud welding for attaching steel decking to structural beams, eliminating thousands of holes that would have weakened critical members. The process enabled composite construction methods, combining steel and concrete in ways previously impractical. Technical evolution refined rather than replaced Nelson's fundamental concept. Modern equipment offers computerized control, automated ferrule feeding, quality monitoring systems. But the basic operation remains identical to 1941 prototypes: spring-loaded stud contact, timed electrical discharge, ceramic shielding. The original design proved so fundamentally sound that major revision became unnecessary. The U.S. Navy Historical Division published an assessment in 1961 examining technological contributions to Second World War victory. The report's Industrial Innovation section stated, "No single process so fully embodied the wartime principle: do more, faster, with less." Stud welding transformed shipbuilding labor requirements while improving quality and safety achievements that multiplied throughout the production system. Economic historians examining American industrial advantages during the Cold War period identified Second World War manufacturing innovations as critical foundations. The ability to produce superior equipment rapidly and efficiently provided strategic advantages that persisted decades after conflict ended. Technologies like stud welding represented competitive edges that potential adversaries struggled to match. Nelson himself continued active involvement with the company bearing his name until his death in 1976. His later years brought industry recognition, including induction into the Welding Hall of Fame and honorary engineering degrees from several universities. But he never sought broader public acclaim, preferring to focus on technical refinement and new applications. Modern welding textbooks dedicate chapters to stud welding processes, teaching principles Nelson developed through garage experimentation. Engineering students learn calculation methods for determining attachment strength and optimal current settings. The technology appears routine and unremarkable to new generations who never experienced the drilling and scaffolding methods it replaced. That mundane acceptance represents perhaps the greatest validation. Truly successful innovations become invisible, integrated so completely into standard practice that their revolutionary origins fade from memory. Stud welding achieved that status. The garage prototype that transformed industrial construction now appears simply as the way things are done. Ted Nelson's quiet persistence changed the industrial mathematics of war. His process did not win battles directly, but it built the ships that carried those who did, the destroyer escorts that hunted submarines, the Liberty ships that supplied invasion forces, the submarines that strangled enemy supply lines. All depended partly on technology. One welder refused to abandon when experts dismissed it as impractical. 50 million saved man-hours, 2,710 Liberty ships, 247 submarines, 6,000 naval vessels total. The numbers document achievement, but they cannot capture the individual decisions that created possibility. A Navy rejection answered not with acceptance, but with $95,000 risk. A peaceful innovation transformed into wartime necessity. A garage workshop that became industrial standard. The ships built with Nelson's technology carried soldiers to victories, supplies to allies, eventually peace to shattered nations. Those vessels fulfilled missions their builders could barely imagine, serving purposes far beyond tonnage calculations and production schedules. But they existed because one individual believed simple efficiency improvements might matter, even when institutions with greater resources disagreed. History remembers the dramatic innovations: radar detecting distant enemies, code breaking revealing secret plans, atomic weapons forcing surrender. These achievements deservedly claim attention. But wars are won through cumulative advantages, not single breakthroughs. The mundane improvements that multiply across millions of operations often prove as decisive as spectacular technologies. Ted Nelson understood that truth intuitively. He never claimed his invention would win the war, only that it might help build more ships faster. That modest assessment proved accurate. Stud welding contributed its share to ultimate victory, not through revolutionary impact, but through relentless, compounding efficiency applied at industrial scale. The final measure of his achievement appears not in citations or statistics, but in every vessel still using the technology he pioneered. Each attachment welded in seconds rather than drilled in minutes extends a chain of influence reaching back to 1941 California. The process continues, unremarked and routine, building the ships that build the future. If you value documented history grounded in verifiable innovation, consider supporting content that preserves and shares true stories like this one, stories of quiet persistence and practical ingenuity that changed the course of history.